Hello everyone, welcome to lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan. I'm an assistant professor at Comsets University, Islamabad, WA campus. These slides have been edited from these two sources. The topics of this lecture are instruction set of Intel family of microprocessors, in particular 8086 microprocessor, and some data transfer instructions, including push, pop, in and out instructions. To understand why do we need instructions, we first need to understand a computer program. A computer program is a set of instructions written to solve a particular problem, and each computer program consists of instruction. Then an instruction are just directions which a microprocessor follows to execute a task or a part of task. Computer programs are written using certain rules called computer programming language. Computer programming languages are grouped as high-level languages and low-level languages. In high-level languages, computer programs are written and using English symbols or letters or words, and they are easy to understand by the computer programmer, but they cannot be interpreted directly by a computer machine. For that purpose, low-level languages are used. Low-level languages are then divided into machine language and assembly language. A machine language, as the name indicates, is the language that the computer machine can understand. In this language, computer instructions or program instructions are a sequence of binary bits which the computer hardware can interpret and then execute a task or part of a task. Assembly language, on the other hand, are instructions written using English alphabets or mnemonics. As these English alphabets are easy for the programmers to remember and to understand, but the computer machine cannot directly execute them. To automate this process, computer programs called assembler are used to translate instructions written using mnemonics to bit sequence or instructions in the machine language. Computer programs, to facilitate computer programs, in particular complex applications, are first written using high-level languages, then they are compiled into assembly language using a compiler for that particular language. Then the assembler is used to translate the instructions in assembly language to bit sequences in the machine language. Microprocessor, in particular 8086 microprocessor, supports 6 types of instructions. The first group of instructions is data transfer instructions. These instructions are used to transfer data from one location to the other, to move data from one location to the other. The other group is arithmetic instructions. These instructions are responsible to perform arithmetic operations, for example, addition, subtraction, division, and multiplication. Logical instructions include instructions that perform logical operation, for example, and, or, exclusive, or, etc. There are string manipulation instructions as well. These instructions are responsible to manipulate string data. They can store string data, they can move string data from one location to the other, and so on and so forth. Then there are processor control instructions. These instructions control the operations of the processor. For example, clearing the interrupt flag or setting the interrupt flag, or clearing the direction flag or setting the direction flag, and there are many other processor control instructions. And finally, we have control transfer instructions that transfer the flow control from one place to the other inside the program. For example, jump and call instructions are in this category of microprocessor instructions. The main focus of this lecture is on data transfer instructions. These are instructions that are used to transfer data or address into a register, into memory locations, and into input and output ports. These instructions can also take data or read data or address from registers, memory locations, and input and output ports. These instructions normally involve two operands, one is source operand and the other is destination operand, and both of the operands should be of the same size. The source of data in these instructions is normally a register, it can be a memory location, and also it can be an immediate data. Immediate data is the data that is provided as part of the instructions, while the instruction can read the data from the registers and also from the memory location, while in the immediate data it is provided as part of the instruction. Destination can be a register, it can be a memory location, but remember that it cannot be immediate data as the destination. The sizes should be either a byte or a word if we are talking about 8086 microprocessor, but in a higher version of the microprocessor, the data size can be long. For example, the size can be a double word, for example, 32-bit. An 8-bit data can only be moved to 8-bit register or memory location, and similarly, 16-bit data can be moved to a 16-bit register or 16-bit memory location. A 16-bit data from a 16-bit register cannot be moved to an 8-bit register because that would lead to an overflow error. In assembly language instructions, memory address calculation is normally needed by the microprocessor to access memory location. And in this memory address calculation, a number of registers, microprocessor registers, are used. These registers may belong to a bus interface unit. This unit is responsible to fetch an instruction from the memory, and there is an execution unit that is responsible to execute that instruction loaded from the memory. So these registers in the execution unit or in the bus interface unit are used or involved in the memory address calculation. To access memory, the 20-bit address called physical address or memory address needs to be calculated first, and then that location is accessed by the microprocessor. So microprocessor instruction would provide different ways to access memory, and those different ways are called addressing modes. And in all memory addressing modes that involve memory access need to calculate or to compute a 20-bit memory address from the offset address and segment value, segment number. So that address calculation begins with taking a 16-bit value from either of the segment registers. These are the segment registers here in the bus interface unit. So for example, if the data segment is being accessed, then the data segment register is accessed first, and the 16-bit value is first taken from the data segment register, and that 16-bit value is then left shifted by 1 hexadecimal digit or by left shifting by 4 binary digits, and that would give us a 20-bit value. So this 16-bit register content is left shifted by 4 binary digit place or 1 hexadecimal place. So 4 zeros are introduced at the right side. So we at the end get a 20-bit value, and this 20-bit value or 20-bit address is the starting address of the segment that is being accessed. To get into a particular location inside that segment, an offset value is added with this 20-bit address, which is the starting address of the segment. So, and the offset value is a 16-bit value that is normally provided using a register, another register, or it involves some kind of addition with other values, or this offset value can also be provided directly as part of the instruction using different addressing modes. To get the physical address, these two values, the segment, the 20-bit starting address of the segment, the 16-bit value from the 16-bit offset value, these two values are added, these two addresses are added, and a physical address or memory address is calculated or computed. This 20-bit memory address is the address where the instruction has to that instruction has to read or store data at that particular memory location. Among the data transfer instructions, the main focus of this lecture is on a push and pop instruction and in and out instructions, and of course there are other data transfer instructions, but this lecture is restricted to only these four instructions: push, pop, in and out. Push instruction is using a special register called the stack register. So it the stack segment, sorry. So it uses stack segment of the memory to store data onto the top of stack. The style or the form of push instruction is to write English word push. Then there is a space, and then there is a single. There is one argument. In that word, one argument or operand can be a 16-bit register, or it can be a memory location. Based on these two types of operands, there are two forms of push instruction. In the first form, there is a In the first form, there is a 16-bit operand as 16-bit operand stored in the register. So this push instruction would push a 16-bit value from this source register onto the top of stack segment. And this involves that, let's assume that stack pointer has a value, stack pointer register has a 16-bit value. That 16-bit address is decremented by 2, so a 2 is subtracted from the stack pointer current content, and an updated value of the stack pointer is computed. Then, as I said earlier, the push instruction is storing data onto the top of stack segment. So the content, 16-bit content from the stack segment register are taken. They are left shifted by one hexadecimal digit, and that is equivalent to multiplying 16 in the decimal system. So this value, this multiplication would give us a 20-bit starting address of the stack segment. Then to get into a specific location inside that stack segment, the updated stack pointer value is added. The 16-bit offset address in the stack pointer is added with the starting address of the stack segment. So this would give us the memory address inside the stack segment. The reason that 2 is subtracted from the stack pointer value is that we have the data, the size of the data is 2 bytes. If it would be a single byte, then we would subtract 1. If there would be a 4-byte operand, then we would subtract 4. So after calculating the memory address inside the stack segment, the 16-bit value in the 16-bit register is stored on the memory address calculated. So the first byte, the rightmost byte, is stored at the memory address calculated here, and the upper leftmost byte is then calculated at the next higher address. So memory address plus 1 is used for that purpose. So this is how the 16-bit value is stored at the stack segment, and how the memory address is calculated. If we at the argument of the push instruction is a memory location, then the stack pointer is decremented the same way as it did for the register operand, and then this in the same way a memory address is calculated, and the memory the data, the 16-bit data at this memory location is pushed onto the stack at addresses calculated here. So the first byte, the rightmost byte, is stored at memory address here, and the next higher byte is stored at the next higher memory address. And this pattern of storing the low order byte at the low byte or rightmost byte at the lower memory location and the higher byte at the higher memory location is called Little Indian pattern. Here is an example of this format of push instruction where push AX. So AX is a 16-bit register. So the 16-bit value in this AX register is pushed onto the top of stack, and here this diagram demonstrates the effect of this instruction. So let's assume the stack pointer, this is the stack pointer register that holds a 16-bit offset address. This is the AX register, which stores a 16-bit value 6AB3 in hexadecimal, and let's assume this is a stack segment register content 0300, and this value is the value after the push AX instruction is executed, and this is the memory state, the stack segment state, which is shown after the push AX instruction is executed. So let's assume the stack pointer content is points to this location 03800. So this is the location where the stack pointer locates to or points to before executing this instruction. So when this instruction is being executed, the content of stack pointer is decremented by 2. So stack pointer would point to this location. So this is the location where the stack pointer points to or locate to. The accumulator has this value 6AB3. So B3 is stored at the location where the stack pointer points to. The memory address would give us this address. The physical memory address calculation would give this address 037FE because that is that offset address which would be here. 3800 would be the value before push X instruction is executed in the S stack pointer register. So let's assume 3800 is the value in the stack pointer when this instruction is executed. This value is decremented, so it would give us 07FE, and the physical address is calculated by appending a 0 with this value, and then the offset address from the stack pointer is added and physical address is calculated, and this is the new physical address. So at this physical address or memory address, the rightmost byte of accumulator is stored, then the physical address is incremented by 1, so you would get to this location, and the next higher byte 6A is stored at the higher location, and the updated stack pointer content would be 07FE because it has been decremented by 2. So currently stack pointer points to this location, and the register content 6AB3 has been written over to the two memory location. B3 is written to the lower memory address, and the higher byte is written over to the higher memory address, and this pattern is called Little Indian format. So this is how push instruction would write or push the 16-bit content over to the top of stack. So initially the stack pointer was pointing to this location, and after this instruction is executed, now the stack pointer points to this location because it has been decremented by 2. So this is the current content of the stack pointer. For the next form, for the push memory form, this is the example push instruction where push AX in the bracket is the instruction. So remember that AX here is not enclosed in the brackets, and that means that the addressing mode used in this instruction is the register addressing mode. But here the addressing mode is a register indirect memory addressing mode, where the offset address is provided through the address is provided through the register. So what happens here is that the X register now holds a 16-bit offset address, and this offset address is the address of the memory location in the data segment addressed by this offset address in the X register. So first, the location inside the data segment is accessed using this offset address, and then a 16-bit value is first from that memory location over to the top of stack. So the rest of address calculation for the stack is similar to the memory address calculation used in this push instruction. But the difference between these two instructions is that here the 16-bit content from the X register is stored onto the top of stack, but here the 16-bit content from the data segment memory location addressed by the offset address in X is stored onto the top of stack segment. For the FOB instruction, just like push instruction, we have the two forms. The operand can be a 16-bit register, or it can be a memory location. Remember that we can also push immediate data, which is not mentioned here, but in case of POP, immediate data cannot be used here. So this would give us two forms of POP instruction. POP, a 16-bit register can be used, and also POP, a memory location can be used. So what this POP instruction does, POP would take an 8-bit or 16-bit value from the top of stack into this register or this memory location. So this is actually this register or memory location is actually the destination of data, while in case of push, the 16-bit register or memory location was the source of data. Here in POP, the source of data is the top of stack, while the destination of data is this 16-bit operand register or 16-bit memory location. Here we have two forms. Either in this POP instruction, there is a 16-bit register as the destination of data, while here there is a memory location as the destination of data. In this case, first the stack segment 16-bit content is left shifted by one hexadecimal digit, or by multiplying a 16 in the decimal system. So this multiplication would give us a 20-bit value, that is the starting address of the stack segment, and then the content of the stack pointer is added, and we would get memory address inside the stack. This S is used for the stack, and then from that memory address plus the higher memory address, 2 bytes are moved to the 16-bit register used here as the destination of data. And after executing this instruction, the stack pointer is incremented by 2. So the stack pointer now points to higher addresses. So remember that in case of push, before executing the push instruction, the stack pointer is reduced by the number of bytes that are to be pushed. While in case of POP, the stack pointer content is, or the stack pointer address is incremented by the number of bytes that have been popped up from the stack segment. And the same address calculation is used in case of memory. The only difference is that the destination of the data, where the data is to be popped to, is a register here, while it is a memory location here. And the address of this memory location, the address calculation for this memory location is not mentioned here, but it is similar to the address calculation used in other addressing modes or in other instructions, where the data segment content is left shifted by 1 hexadecimal digit, and an offset address is provided here is added with that 20-bit address, which is the starting address of the data segment, and bytes are then written over to those to that memory location and the next higher memory location. As an example here, for this case where POP BX is used, so The source of the data is not mentioned, but that is implicitly there using the stack pointer in the stack segment registers. But the destination of data is 16-bit register BX. So this is the state of a memory stack segment and some of these registers after executing the pop BX register. So let's assume we have this BX register, and this stores some different value which is not shown here. This is the value after this pop BX instruction is executed. So let's assume stack pointer points to this location, and the stack segment has this value. So this value is then left shifted by 1 hexadecimal digit, and a 0 in the hexadecimal is introduced at the right side. So we would get a 20-bit address here, and this 20-bit address is this 20-bit address, an offset address from the stack pointer is added with this 20-bit address, and the stack pointer value shown here is the value after executing this instruction. But before executing this instruction, the stack pointer value would be 1006. That 1006 is added with this one, and this addition would give us 01006 as the memory address or the physical address inside the stack segment. So the first byte at that location, 2F, is loaded at the lower byte of the BX register, which is BL, and 2F is loaded here, and then this memory address is incremented by 1, and it would point to the next higher location where 39 is then loaded to the high byte of the BX register. 39 is loaded here, so 39 to F is moved to BX register, and the stack pointer is then incremented by 2 because 2 bytes have been added. So the stack pointer content initially was 1006. When a 2 is added, it would become 1008. So at the end, the memory, the stack pointer would point to this location because the stack pointer has been incremented by 2. So now the updated value after executing this instruction is 1008. So the stack pointer now points to this location. This is the location where the stack pointer points to. So this is how pop BX would pop 16-bit value from the top of stack and would store it into the BX register. For the push, there are a number of other forms of instructions for 8086 microprocessor and later microprocessor. So this instruction push register 16, this we have just seen an example of this. So push BX, this would push this 16-bit value onto the top of stack. Push register 32, the 32-bit register is used as the source of data. So this 32-bit value in this extended version of the DX register is pushed onto the top of stack. Remember that EDX is not available in the 8086 microprocessor, but it is available in the later microprocessor. Push memory 16, if one want to push a 16-bit value from a memory location provided here, then the microprocessor needs some additional directives to tell the microprocessor that only 2 bytes of data is to be pushed from the memory location given here onto the top of stack. So this BX register now holds the offset address of the memory location inside the data segment, and the 16-bit value from that memory location is pushed onto the top of stack. This word PTR, word pointer, is used to guide the microprocessor that only 16-bit data is to be taken from this memory location and to be pushed onto the top of stack. If 32-bit data is meant, then a 32-bit address is provided here as the offset address, and in this offset 32-bit register would give us 32-bit address, and a 32-bit value, this double word pointer means a 32 4-byte value is taken from that memory location and is pushed onto the top of stack. Segment registers can be pushed. For example, data segment register is pushed onto the top of stack, an immediate value. For example, the ASCII value of this comma is pushed onto the top of stack. A 16-bit 16-bit immediate value can be first double would first this immediate value as the 32-bit value. We can push all 16-bit registers. All the 32-bit registers can also be forced onto the top of stack. Flag can also be forced onto the top of stack, and E flags available in some later microprocessors. Flag double, which means that E flags, which is 32-bit flag, can also be forced onto the top of stack. So these are a number of variations of the push instruction. Similarly, there are a number of variations for the FOP instruction. For example, this FOP register 16, we have seen an example of this. So a 16-bit value from the top of stack is popped up from the top of stack and is stored in this CX register. Similarly, 32-bit value can be popped from the top of stack and can be stored in this register. And similarly, 16-bit value from the top of from the top of stack segment can be taken and stored on this memory location. And similarly, 32-bit data can be taken from the top of stack and can be stored in this memory location. Data 3 is a variable which points to a memory location. Similarly, segment can be popped up from the memory from the top of stack and can be added in the FS segment register. All 16-bit register can be popped up from the top of stack. All registers, the 32-bit versions of all the registers can also be popped from the top of stack. And similarly, flags can also be popped from the top of stack, and the 32-bit versions of the flags can also be popped up from the top of stack. Remember that pop is not available as an immediate pop. There is no pop followed by an immediate operand. For the pop, there must be a register or memory as the operand, as the source of the data. Similarly, POP-C is not a valid instruction. You cannot pop from the top of stack to the code segment. Otherwise, it would change the flow of the program, and this is not allowed, and this is not a valid instruction. Just like push and pop, there are in and out are also data transfer instructions. In the N, there is a register and there is a memory location. There is another register that provides the address of the input port. So this the address of the input port is provided indirectly through a register, and this address can also be provided directly using the direct port addressing. So in this instruction, this is the port address. That port address would identify an input port from where the 8-bit data is to be read from. For example, this is one case where DX provides the port address, and DX provides the port address. So the data, an 8-bit data from this input port is loaded into the accumulator register L. And in this case, a 16-bit data is read from this port address, which the address of this port is provided indirectly through the DX register. So this DX register basically stores a 16-bit value, and that 16-bit is actually basically the 16-bit address of the input port. And a 16-bit value is read from that 16-bit from the input port identified by this port address. Similarly, in this form of addressing, NA address 8, which provides port address, but that is directly provided as part of the instruction. So this is direct port addressing, this is indirect port addressing. So in this form of addressing, an 8-bit port address is used as part of the instruction that would identify the input port from where 8-bit data is to be read, while here in this case The 8-bit port address would identify the input port from where a 16-bit value is to be read and loaded into the AX register. Just like the input instruction that reads data from the input port, and the port address may be provided indirectly through the register, or it may be provided directly as an immediate port address value. Just like that, out instruction sends data from accumulator to an output port, and their data can be 8-bit, their data can be 16-bit, and the address of the output port may be provided indirectly through a register, or it can be provided directly through an immediate address. So here in this example, the 8-bit content from the accumulator AL register is written to the port, output port, addressed by the this register indirectly. So AL is written over to, or the data in the AL register is moved to this port addressed by the DX register. And here the 16-bit content from the X register is written to or moved to the port addressed by indirectly addressed by the DX register. While here accumulator is written over to the port output port addressed by immediate 8-bit address here. So here in this example, 8-bit L is written to the port addressed by this 8-bit address, while here 16-bit content from the AX register is written over to the port output port addressed by this 8-bit address port address. So just to summarize, in the N instruction reads data from the input port, and the data can be an 8-bit or it can be 16-bit. The port address can be indirectly provided through a register, or it can directly be provided by providing the port address directly as part of the instruction. Similarly, in the case of out instruction sends data from the accumulator to an output port, and their data can be 8-bit, their data can be 16-bit. The address of the port can be provided indirectly through a register, or the address of the port can be provided directly as part of the instruction. So these are some instructions that we just talked about them in this lecture: push, pop, in and out, and there are a number of other data transfer instructions. For more detail about these instructions, please refer to the textbook of microprocessor systems and interfacing. And if there are any queries or questions while watching this video, please keep a note of them. You can ask those questions and queries during the online session. Thank you.